So if you calculate the polarity the same way we did last week, you find that both bonds are polar. You've got an uneven arrangement. That means that we can figure out that this end of the molecule is going to be polar, and if we did the math, we could find out that this end of the molecule was nonpolar. CH groupings, and this is something we said in Unit 4, CH groupings tend to be nonpolar. Please stop. Okay, so. Say what now?
Like if one side is polar and the other one's automatically going to be nonpolar?
Not necessarily, but in this case it is.
Okay, so
These
can be both polar and both nonpolar?
In this case we have a molecule that's both polar and nonpolar. One end is polar, one end is nonpolar. That's what you need to know from this activity. Now, what that means is that this molecule, CH3, CH2, CH2OH, is attracted to another molecule of the same type.
I got a question. How is it polar to... Oh, never mind.
So this is a dipole-dipole attraction between those ends of the molecule. A dipole-dipole attraction between that end of these two molecules, or those ends of those two molecules, because that end of the molecule is polar. This end of the molecule is not polar. So any attraction between this end of the molecule and this end of the molecule is due to London force attractions. Okay? Okay, let's be clear. What we're talking about here is polarity in larger molecules. And what we're finding out here, what I'm hoping you're understanding from this, is that in larger, we've been dealing with small molecules up to now, but in larger molecules, I can have both polar and nonpolar parts of the same molecule. Okay, that's very important. That's a very important concept for you to understand. Chandler, can't behave. I can move you or send you out. Okay. All right. Is that clear enough? Do you get the idea? Well, let's find out. Okay. Let's remind a little more, and then we'll turn you loose on a problem for you to do in groups. Okay. Shh. Last week, twice last week, I went over this idea that I'm going to review with you again. When we were looking at smaller structures, at the simple structural particles and the results that you get from those, we found that we have five categories of structural particles. We had nonpolar molecular particles, which make nonpolar molecular structures. We had polar molecular structures from polar molecular structural particles. I would suggest you would, yeah. We had ionic structures from ionic attractions between ionic particles. We had metal structures from metal attractions, and that theory is called, or that model is called what? Anybody remember the electron C model, which describes the way that metals are stick together? Okay, and then we looked at covalent network compounds. And when we looked at those, we found that the strongest overall structures resulting from those attractions were the covalent network compounds. And they were strongest because of the overall attraction between those individual particles. So the glue that holds it together is stronger. Okay? The weakest was the nonpolar molecular attractions. The force that holds those together we called London forces. That was the result of a temporary shift in electron density. We explained that and went over the theory last week. And in between we have polar molecular. Polar molecular resulted from permanent shifts in electron density, permanent densities of electrons that are greater on one of the molecule than another, ionic, metallic. And so you also get, because of those stronger to weaker attractions between particles, you get really high melting and boiling points up here, really low melting and boiling points down here, and it ranks from lowest to highest. Lowest boiling and melting points to highest boiling and melting points. But what we're looking at right now, and what we looked at just a moment ago when we looked at these two kinds of molecules, are that we've got a whole range of things in between these two. Okay? We're not looking at these as if this is a black and white issue or a brown and tan issue. We're looking at something that is, sometimes this and sometimes this and sometimes in between those things. Okay? You got stronger nonpolar and stronger polar attractions between particles. Okay? So here's what I'm going to let you do. We're going to use the same groupings we used when I was out last week.
You watching video?
No. And I'm going to ask you to figure out in your group. I want you to figure out in your group. Well, let me see. Let me do one more thing before we do that. Let me give you a little test here on one thing before we turn loose on something else. Let me give you a little quiz yourself question. Okay, let's do this. Chandler, be quiet, please. Just wait. So here are 5 different compounds, 5 different structures, and I want you to rank them in terms of which one would have the highest boiling point to which one would have the lowest boiling point. Which one's going to have the highest boiling point and which one's going to have the lowest boiling point. Find a pattern to tell you which one has the highest boiling point, which one has the lowest.